So in this video we are going to solve problem 6.35. It has letters A, B, C, and D. So the first circuit that we have is this one here. We have two resistors, the collector resistor and the emitter resistors. They're 2.7K. The base is grounded, and our VCC plus VCC and minus VCC are 1.5 volts. So the problem says that VBE, the magnitude of VBE is 0.8 volts. So in this case, because we have a PNP transistor, an NPN transistor, because of the arrow, we know that we have the emitter here, right, the collector here, and the base here. So in our case, we can assume active mode operation because VBE is 0.8 volts. So we know that VB minus VE is equals to 0.8 volts, assuming active mode operation of the BJT. And in this problem we need to define all the currents, so we need to find out IC here, we need to find out IE here, and the base current here, IB. And the voltages at the base, collector, and emitter, so VC, VE, and VB. Okay. Now, one thing is that if we look at the circuit, right, here, the base is grounded. So if the base is grounded, the voltage at the base, VB, is actually 0 volts. And that's one of the answers. The voltage at the base is equals to 0. Now, because we know the voltage at the base, we can substitute up here the voltage at the base and we can calculate VE. So in this case, VE is equals to minus 0.8 volts. That's the second voltage. Now we are not able to conclude about VC yet, but we can start calculating some currents now. Because if we look at the emitter terminal here, we know VE is this voltage here, and we know this potential here, right? It's minus 1.5. So this potential difference here, we are able to calculate. And if we know that potential difference, we can calculate IE. And so the voltage across that 2.7K ohm, right, is, let me write here, sorry, 2.7K. is equals to VE minus those minus 1.5 volts, right? And that's equals to the emitter current times 2.7K. So IE is equals to 1.5, right? It becomes positive here. VE, we know that it's minus 0.8, so it's minus 0.8 divided by 2.7K. This gives us IE equals to 259.2 microamps or 0.26 milliamps. Okay, but I like to use this engineering notation here, and that's the value of the current, IE. Okay, so we know this current, we know the voltage at the emitter, the current at the emitter, we know the voltage at the base. Now, because we are assuming active mode operation, we can calculate the current at the collector as alpha times the current at the emitter. And if we calculate alpha from this circuit, okay, from beta, we know that alpha is equals to 50 divided by 51, which gives us 0.9803. So IC is equals to that 0.9803 times those two 59.2 microamps. This gives us an IC that's equals to 254 microamps. Okay, this is IC. Now we know IC, we know IE, we can calculate the base current. So the base current is just IE minus IC, and that's equals to 259.2 minus 254 microamps, which is 5.2 microamps. So this is IB. So we know all three currents. We just need to calculate the voltage at the collector. So the voltage here, VC. Now we know this potential here, right, is that plus 1.5 volts. We know this current here, right? We can apply the same methodology that we applied on the emitter. So the voltage at 2.7K, and remember that this is at the collector, so it's equals to that 1.5 minus VC, which is the same as 2.7K times the collector current. So this one here we know. We just need to define VC. So VC is equals to 1.5 minus 254 microamps times 2.7K, which is equals to 0.8142 volts. So all 6 quantities are defined for this circuit. Now if we go to the next circuit, we have a similar topology, but now the values of the resistors have changed. And if you look at the BJT, it's not an NPN BJT anymore, it's a PNP BJT, so PNP. And for a PNP, we know that we have VEB equals to 0.8 volts. So in this case, VE minus VB is equals to 0.8. And if we look at the circuit again, here at the base, right, we are grounded, so this voltage here we know, VB. So let me use another color. So VB is equals to 0 volts. That's one of the quantities, right? And if we substitute this one up here, we can calculate VE. So let me write VE here as 0.8 volts. That's the second voltage. And basically we applied the same methodology, right? So we know VE, this one here, we can calculate this current here, IE, at the, sorry, this is not the emitter, because it's a PNP. So for a PNP, VE is this voltage here, right? Because here we have the emitter, the base, and here the collector. So this is actually VC. So we know this VE, we can calculate this current here, IE, right? And that current IE is equals to 1.5 minus the voltage at the emitter, 0.8, divided by 2K. And that's 350 microamps. So that's a third quantity. And again, we can calculate the collector current using the common base current gain, alpha. So IC here is equals to alpha times IE, which is the same as 0.9803, because remember the beta for this circuit is the same as for the previous one, so it's still 50, and that's times 350 microamps, which gives us IC equals to 343.1 microamp. And let me see, we know IC, so if you know IC, let me go to the circuit again. So remember, the collector is here, right? Here. This is VC. And we have the collector current flowing down here. So this is IC. And we can calculate this current. Basically, we know this current. We can calculate VC actually by calculating this potential difference here across this 2K ohm resistor. So we know that the voltage across this resistor is equals to, let me use green again, so is equals to VC minus 1.5 volts, right? Terminal here, and that's equals to IC times 2K ohm. So if we isolate VC, VC is equals to IC times 2K ohm minus 1.5. If we substitute this current here, we get VC equals to minus 0.813 volts. So let's see, we have IC, we have IE, we have VB, VE, and VC. We still need to calculate the current at the base, right? So the current at the base, let me pick blue here for the base. So the current here at the base is equals to the current at the emitter minus the current at the collector, which gives us 350 minus 343.1. And remember, this entire stuff here is microamps. So IB is equals to 6.9 microamps. Okay, and we could still verify that VCB is less than 0.4 volts to agree with our assumption of active mode operation. And because we know that VB here is 0, basically VCB is VC, right? VC minus VB gives us minus 0.813 volts, and that's actually less than 0.4. Okay, so 0.813 less than 0.4. That agrees with our assumption of active mode operation. Okay. Now the third circuit that we have, now the emitter is grounded, right? Because it's a NPN. So if you look at the circuit NPN, right? No, it's a PNP. Sorry, it's a PNP again. So this one here is a PNP. So we have our emitter here. We have the base here, and we have the collector here, right? So we know from PNP that VEB is equals to 0.8 from the problem. We know that VB, so let me use here, so if we look at the circuit, we know that the voltage here at the base is this 1 volt, right? So that's one of the quantities that we need to calculate. So we know that VB is equals to 1 volt now, because it's not grounded anymore. And this potential here, 1 volt, forces the voltage at the base to be 1 volt. And if we expand this one here, we can actually calculate the voltage at the emitter, right? Because VE minus VB is equals to 0.8. So we can substitute this one here, and our VE is equals to 0.8 plus 1 volt, right? If we put this one here on the right hand side, which is 1.8 volts, which is the second quantity that we need to define here. Now, because we know VE, right, so we know this potential here, we know VE here, right, we can calculate this current IC. So IC is going to be those 3 volts minus the voltage at the emitter, which is 1.8, divided by the 10k. So IC is, oh sorry, IE is 120 microamps. So we got IC. Again, we can calculate, sorry, it's not IC here, it's the emitter. Okay, so we are calculating, so this one here, I write IC, but it's IE, okay. It's just that sometimes it's confusing when we change from PNP to NPN in the same problem. So this is IE. Okay, now we can calculate IC using alpha again. So this is 120 times those 0.9803, which gives us, let me see, 117.63. 17.63 microamps. This is IC. Now, since we know IC here, right, we can calculate VC. And VC is equals to, because here is 0, right, is grounded, so VC is actually the voltage across the 5.6k ohm resistor, which gives us that IC times 5.6k. If we substitute IC up here, so this one here, right, we get a value of 0.658 volts. This is VC. And then IB, so IB, which is the last quantity we need to define, we can calculate again by the difference of IE minus IC, and that is 2.37 microamps. So all those problems, they are pretty much similar. You must be careful by identifying the type of the transistor, okay? But on these problems here, they are very similar. So the last problem on this exercise, we have now an NPN. So now it is an NPN. So we have the emitter here, we have the collector up here, and we have, sorry, let me use the same colors, try to use the same colors. So the collector up here and the base here. Now because it's a NPN, we know that VBE is equals to 0.8, right? And that's from the problem. We still have beta equals to 50. Now if we look at the base here, we have this 1.5 volts that's been forced as the base voltage, right? So VB is equals to 1.5 volts, right? And we are not using any equations from the BJT analysis. It's just like looking at the circuit and identifying that VB is 1.5 volts because there's a voltage source here that forces that to be true. Now, because we have VBE equals to 0.8, it means that VB minus VE is equals to 0.8. And if we substitute VB here, we have VE equals to 1.5 minus 0.8. So VE is equals to 0.7 volts. And because we know this voltage here at the emitter, and we know the potential here at the other terminal of this 4.7k ohm, we can calculate this potential difference and we can define a current here, IE, right? So this current IE is going to be VE minus 0 volts divided by those 4.7K, right? Just using Ohm's law. So VE here we know that's 0.7. And if we take that 0.7 divided by 4.7K, we get 1.49 microamps. And this is IE. Now, because we know IE, we can calculate IC, right? Using the common base current gain, alpha. So at the collector here, right, we can calculate the collector current as alpha times IE. And this gives us 0.9803 times those 149 microamps. So IC in this case is 1. Oh, sorry, no 1. It's 146 microamps. Now if we note this current here that's flowing at the collector, IC, we can calculate VC by just analyzing the potential difference or the voltage across this 8.2K resistor, right? So VC, okay, or let me write the equation for the potential difference. So we know that 3 minus VC, right? This one here, VC, this one here is 3 minus VC divided by those 8.2K should be equal to the current IC. Or in other words, VC should be equals to 3 minus 8.2 times IC, 8.2K times IC, which gives us now VC. So if we substitute IC here, right, VC is 1.8 volts. And the quantity that's left is IB. So okay, what's the current IB here? Now remember that we have IE flowing down here, right? So let me just make this more clear. And we have IC up here. And we know that IE is equals to IB plus IC, so IB is equals to IE minus IC. And if we substitute IE and IC in this equation, we get IB equals to, so this one here is 149 minus 146 microamps, which gives us 3 microamps for the base current. There's other equations that we can use to calculate the current at the base. So one of them are that we know that the current at the collector is the same as beta times the base current, right? So if we know beta, we know that from the problem, so we can use that to also to calculate IC. But you see that once we know IC and IE, it's just a matter of taking their difference and then you calculate IB. But there are like other ways to find out some of those quantities, okay? So there are like multiple solutions, okay? Eventually, I mean, the final results, they should be the same, but there are a lot of like ways paths you can follow to get the same answer.